Yeah, that's fine. And if we want to do this, I just say escape, and I want to put something else up there right now. Here's the syllabus.
Yeah, you can write on that as well. The same process you will do.
Okay.
Okay.
All right. Anything else? All right. How are we doing? So did I scare you or not? All right. So number one, I want to show you the syllabus. I guess all of you have a copy of this. We try to kill, or at least I try to kill as less tree as I can. So everything is electronic. If you want to print it out yourself, go ahead and do it. Syllabus is very well written. So can somebody tell me what this course is all about? Yes?
Provide a foundation for engineering math.
Yeah. Why is that important? What did we learn the last? Yeah, go ahead.
Because there's such a high dropout rate of engineers, it's going to get us ready for the next 4 years instead of starting our classes our junior, senior, 2 years on the way.
Right, right. Now we all already know that it is the excellent return on investment when it comes to engineering degree, right? So we all know that it's a good marketplace out there and so forth. But like any other thing, it's not easy. Obviously, it's not easy. But what you learn, of course, is just going to be with you. There's hardly anybody out there who started as engineering and is really not refer back to it every now and then. It's a really foundation, not only foundation for your professional, but also your way of living. I mean, engineers have certain attitudes, and our attitude is extremely positive, but at the same time, it's extremely skeptical, because obviously we're never 100%, but the reality is that we are the builders of the future. And this goes back to more than 5,000 years ago. When you're looking at the pyramids and how any human being can build something like that. How many of you have been to Egypt? Have any of you been to Egypt? Now, when you look at these big structures, really huge structures, as big as a World Trade Center, and you feel that this was built 5,000 years ago, then you wonder, how on earth can anyone build something like that when there was no electricity, no internal combustion engine, none of that? How can that be possible? And that's really the essence of engineering. Without math, it cannot happen. So my objective in this course, and other people who will be helping you out as well, is make that connection. So because most of your math courses, if not all of your math courses, is going to be taught by math department, right? How many bridges do you think they have ever built in their life? How many planes have they designed? How many oscilloscopes they have ever seen, let alone designing them? They do know the theory and so forth, but we are the application people. So the idea is to show you that what you're learning over there has a connection. And if you feel frustrated with them, think about later on. So in my course, when I'm when I'm putting these examples, and this book that you have is all about examples. It's not teaching you the fundamentals, but it's just giving you examples, hoping that you all understand the examples. And if you don't understand, just tell me, okay? And I'll try to explain it to you. How many mechanical engineers here we have? Electrical, civil, environmental, bioengineers, engineers. See? You're all here. Community of one. It does not really matter what discipline you are. Foundation of engineering is right here. And that's what we're covering. So looking at your syllabus, familiarize yourself. I noticed that there is still about 3 or 4 of you that have not gone to Blackboard. Please do. This is a means of, I guess, communication between us, but I want to bring it down to this schedule here. How many of you have seen this schedule here? Why have I spelled it out for you? Why? Yes. Exactly. Exactly. Don't leave it, for the next day or the day after. I know about the, Thursdays, Thursdays, party Friday, Saturday, and then, hangover Sunday. Don't do that. This is it right here for you. Be ahead of the class. You know why is it important? Because when you're doing this, then when you come to my class, you are full of questions. Full of questions. I try to answer those questions here, but if I don't, ask that question. Because really this is all about. Because all I can do is just put whatever you have in your book and say, okay, let's go home. You can do it on your own. No, that's not the intention. And I never open up the book and say, look at this, look at that. Because, you're intelligent. You can all go do that. Here is a matter of communication, talking to each other. Look at those problems. So when I'm looking at homework number 1, for example, 3, 14, 20, what does that mean? Yes. That's only 3 questions. Somebody was asking me, are you telling us that we have to solve from 3 to 14 to 25? I said, no. I thought this is very clear. Is this clear? Right. There's only 3 problems from chapter 1 and 3 problems from chapter 2. That is your homework from me. Does that mean that you should ignore everything else? No. Please don't. But this is at least the minimum that I expect you to do. The minimum. And believe me, I've selected it quite randomly. So some of you might think, okay, this is where the exam question is going to come from. So that's all I'm going to learn. I can make you one promise. Exam's not going to come from there. It might be related to them, but I want you to look at them as something to get you going. I'm sure you're going to enjoy it. And exams are there, I'm putting things like that this is the date that you can drop out. I hope none of you do, because that's not the intention. And of course, any time in between. And then you have your labs spelled out. Hopefully we'll stick to this timeline. On Friday, I guess you're going to get some clarification on that. But if you have any questions, just shoot me an email. Has anyone sent me an email? The answer is yes. Have I not answered anyone? Raise your hand. You communicate with me and I did not respond. There you are. So you send me an email, you get an answer. Okay, and I'll resolve your questions and any issues that you might have. Okay, going back to this. So hopefully, so the last time that we saw about the straight lines, do you remember what this equation was about? Yes. Velocity of a function of time. But do you remember the problem that we dealt with? Yes.
Car was coming to a stop.
Right. A car moving. Something moving. And it was on a straight line. And of course, velocity was a function of time and the time that it took the car to come to a complete stop. So the next thing for us was a question for you. Let's see how awake you were last lecture. What is the answer to this? Yes. D. How many people agree with the answer D? How many people disagree? How many people are awake? Good. The correct answer is D. That means you were paying attention. All right. So the next example is, yes, thank you, electrical devices. Now, how many of you have seen this? Can somebody explain to me what that is? A circuit. So which of, what do we mean by VS, V sub S?
Supply.
Voltage supply, yes, voltage supply. Can you give me an example?
Like a 9-volt battery.
There you are, a 9-volt battery. What kind of a current am I showing here?
Direct current.
Direct current, right. How many people understand what the direct current is? Can somebody explain to the ones that are not raising their hand, what is the direct current?
You're getting a singular voltage supply that's a constant voltage, unlike alternating current, which goes through a sine wave. So usually you see 3-phase, so you have 3 sine waves working together to create a amount of electrical potential known as voltage, usually 120 volts in America.
Who invented DC? Yes. Tesla was AC actually, but Tesla was working in the lab. Edison, right, Edison. In fact, the first electricity generator was DC. He thought that he's going to go make millions, but of course Tesla, working in that office, said wrong, and the AC basically take over. But the voltage source that we have basically shows positive and negative, right? You know, you've seen batteries, positive and negatives, going to something called R. What is R? Yes. Resistor. Resistor. Can you explain to me what a resistor is? Okay, how? Okay, so the amount of voltage going through it. So you will have a voltage drop in the resistor. And how is that shown? It gets hot, right? Do you have an example of that? Something that when electricity goes through it gets hot?
Light bulb.
Light bulb, anything else?
Charger?
What else? Yeah. Yeah, so there you are. And of course we have a voltage source that basically takes care of the remainder of the voltage. So what we have here is within that resistor, a governing equation is V sub R, which we know it as Ohm's law. How many people have seen that equation? Good. So what does that mean is that the voltage difference or the voltage drop within a resistor is based on 2 items, I and R, which is I is current and R is right. The way we measure resistance is by ohm, the omega sign. Do you see that? The omega sign. How many of you have seen that? Can somebody give me an example of a a value for that ohm? An instrument, yeah. That's the ampere. I'm talking about ohm. Something that you use, I'm sure all of you use, that we can identify the amount of resistance that it has. Speakers. Have you looked at the speakers? 8 ohm speakers, 16 ohm and so forth. It talks about that. And right there. And of course the voltage. So the governing equation that we have in this, and like any other system in engineering, we are interested in equilibrium. So this system must be in equilibrium. That means if it's not in the equilibrium, it breaks up. Like a mechanical system. It breaks apart. So you need to have some kind of an equilibrium in this place. So this equilibrium is identified by Kirchhoff's law. Kirchhoff's voltage law. Electrical engineers are they think they are smarter than anyone else, and naturally whatever they invent, they name after themselves. So, yeah, we have it in mechanical too, Newton's law and so forth. So when they discover something, they're going to put their names right on it, so you will never forget. But the whole idea is that the sum of the voltage increases or the voltage rises should be equal to the voltage drops. So if I am looking at this point here, at this point, maybe I use this item here, at this point there, and up to that point, there is a voltage increase because I'm going from a negative to positive. And that voltage increase is simply V sub S, which is your voltage source. But when I get to this point, and I'll go across R, I'll go across R, then what we have is a voltage drop because we're going from positive to negative side. So the voltage drop in there is equal to V sub R through that resistor. And then we add to it whatever drop we have in the V. So the equation basically converts to V sub S is equal to V sub R plus V, or simply Vs is equal to IR plus V. Okay? So this is basically representing a course that some of you, or maybe all of you, will have under EE 2112 in this college. You're going to see that. Electrical Devices 1. Everybody takes it, and you're going to see that circle right there. What does that remind you of? Reminds you if Vs is equal to IR plus V, which is very much like a linear system. Now, it is quite possible that we get to a situation where, let's go back to there to show you that in this case, what is usually measured. So if the experiments that you're going to be conducting in your lab, for example, when you go to the circuits, the experiments that you're going to measure things, what do you measure in those? You measure the voltages and you measure the currents. So there are two times. You remember that velocity and time? 2 points in time we measure the velocity and at a certain time. Here we have a current and we have a voltage. So if I, for example, put a 9-volt battery in there and I measure the current, then I put a 10-volt battery in there and I measure the current. Why do I do that? Because when I'm measuring it, I want to find out how much current is going through the system and what is the value of V. So for doing that, there are 2 points that I can, for example, identify in the example. I say, okay, when I am putting a 10-volt battery in there, the current that I'm measuring is 0.1. How do I measure current? And has any of you ever measured current? Yes. What do you do?
Use the fluke,
Which is a?
small handheld device that measures current.
Right. Is a meter basically that you use, potentiometer, that you use to measure current. So in your experiment, you're going to do that. You're going to find 2 voltages there and then find the current that is going through it. So why am I doing this? Because I want to find out, what am I supposed to find out? I'm doing so to find out what the resistor is and how much was the value of V in that circuit. Going back to this, you have a voltage system that is based on the current and the value of the resistor, and all I'm doing is I'm putting 2 values in there to find out 2 unknowns. Can I show it this way? Why am I showing it this way? Because in this equation we have a dependent variable and an independent variable. Because you're varying something so that you can measure something else. Now, in this case, obviously, we're putting 2 values of Vs and a current in order to find the value of R and V. And I show it this way because I want to basically compare it to something that you have seen before. Do you see that? Do you see the relationship now? So what kind of a system is this? Linear system, same as before. Exactly what we just had, right? Exactly like, so if I'm going to plot voltage against current, what do I expect to see? A line. That is why we call it a linear system. Do you follow so far? Good. So, how do we measure the slope? You remember that, the slope? Delta y is over delta x. In this case, we said y is equal to mx plus b is same as v is equal to ri plus v, right? So the delta y here basically is the voltage difference in your voltage source. Two different batteries you put in there, and then you want to basically compare it against the current drop that you see. In this case, I'll put the values in there, and I get the slope of 10. So this is the slope of a line, right? The line that represent, and then the next thing is that we want to find the intercept. What was the intercept? Do you remember what the intercept represented? Yes. The initial starting point, exactly. Of course, some places the initial starting point might be 0. So in this case, what we have is we have Vs is equal to 10I plus B, right? So what should I do now? Because in my case, I really want to find something, and that's the intercept. What should I do? We had two, yes. Yeah. Does it matter which one? Doesn't really matter. So I pick one up and I put it in there. See what happens. So now I have the equation of the line. V sub x is equal to 10I plus 9. How many of you do not understand how we arrived at this answer? It's okay. So the point slope form basically was like this. Any point that we put, we would find the values, and obviously this would be the equation of your line. What is the slope of this line? 10. And the intercept? 9. So, there you have it. Do you agree? So now I found the value of the resistor, and I've found the value of the initial voltage, or what we call it the unknown voltage. And those were the 2 points that I selected. So another application of a linear equation in a different field. Before we did it in dynamics, now we did it in electricity. So the question is, what is the dependent variable? Can somebody explain to me what is the dependent versus independent variable? Yes?
The dependent variable would change depending on what your x value is.
Right. So in the y is equal to mx plus b, which one is dependent and which one is independent? Yes? Okay. Is that, do you agree? So, there's no pen here. So, we have y is equal to mx plus b. So you say that the dependent is b, but the b is constant. Yes? Okay. Yes?
Dependent would be m, and independent would be b.
Remember, these are constant values. So the two things that we're talking about is y and x. The dependent is y. Why? Because as you change the value of x, the value of y changes, depending on these two constants. Right? So in this case, what we have is 10I plus 9. So considering this, you would say, okay, then what we are saying is that the dependent is the voltage source, and the independent is the current. Where in reality what we are doing is we are changing the voltage source, we're putting a different battery, and we're measuring the current. There's something, is wrong here. Because in fact, what we're saying is the Y is the, do you understand what I'm talking about? You have a circuit, and in that circuit you want to change something. How can you change the current without changing the battery source? So the only thing that is available to you is to change the battery source in order to measure the current. So there is something wrong with this formula. Yes? Exactly. So in other words, your dependent is I, and the basically independent is the voltage source. As you change the voltage source, so all we have to do is just manipulate this a little bit. So what do? We manipulate it a little bit. So we can represent it this way. So all I do is divide both sides by 10, move it around, and now I have current is equal to 0.1 Vs plus 0.9. Is this still a linear function? Yes, it is still, but the constants are not different. The slope is different, and the intercept is different. But the values are still valid. You can put those values of I and Vs in there. So what I'm telling you is math tells you one thing, engineering tells you something else, but they are interrelated. All you have to do is manipulate it to a form that makes sense to you. So before, mathematically, we were accurate. Mathematically, we basically plotted Vs against I. But from the engineering point of view, we were inaccurate. Because what we were saying there was that the dependent function was your voltage, and your independent was the current. Which in reality, there's no way that I can change the current without changing the battery. Do you follow? That is one, yes. Most probably, I think you're right. I think that's -9. You're absolutely right. -9. Make that correction here. So do you follow what I'm talking about? So it is important for you to really make that connection. Don't take it as is, because, again, mathematically, your math professor is going to say, well, you got the right answer. But your engineering professor says, that does not make sense to me. There's no way you can go to your lab and then be able to change the current without changing the voltage source. So you need to change the battery first before a different current goes through your system. Yes?
What about using a variable resistor?
Variable resistor, as long as so what you're saying is, in that case, you're basically changing your unknown V. Yeah. But that is basically you're messing around with your constant. I'm saying your constant remains constant. Your resistor is the same, your voltage source is the same. So the only way you can change the current is you change the battery. Because, otherwise you got to go and put a different lamp there. So that, the outcome would be the same. Or you would have one of these rosters that you can actually change the amount of current going through your resistor so the light goes up and down, like a dimmer. Okay? So basically, the question is this the same? And the answer is no. They are not the same line, but they are applicable to the same problem. So what we have here in this equation, of course, this is a -9. You can still put the same points that you had before, and you get the same answer. So if I'm plotting it, I'm plotting the voltage source against the current. What is the current measured at? What is the unit of current? Amps, which really comes from ampere, again, another person's name, amps. And voltage, of course, is volts. So, if I am plotting that line, so remember, Vs equals to 10I plus 9. And that is volt, actually, not I. That needs to be corrected. So, where do you think on this V-axis the line will start at? Yes? 9? Is that, people agree? And what about the I? Where would it cross the I-axis? Where would it cross? Come on, give me an answer. He's right in front of you. Yes. Say it. It's okay. It's okay to make mistakes. Yes.
Would it be when it equals to 0?
But Vs would be equal to 0. But then what is the value of I? Yes.
0.9.
Minus 0.9, right? Is that or 0.9? That is your line. Where would this cross? -9, which is coming from there. You put V sub S is equal to 0. So 10I plus 9 is equal to 0. You take 9 to the other side. It becomes -9 divided by 10. That's minus 0.9. That's why the line starts from right here. All of you expected the line like that, right? But your curve is a line. Any questions so far? One final example on the linear. I thought maybe I'd give you an example in the physics. And you're going to see this in those of you who are taking physics, you will see it. This is where you have a preloaded spring. And the preloaded spring, the force that you put in, the relationship between the force is simply based on a spring constant. And the value of the spring constant is Newton per meter, which in physical term means that if you have a spring, it has a shape that is preloaded. And as you pull it, what is the tendency? To pull back. So to pulling that back is based on that formula. That as you extend the spring, a force will be generated that would oppose that movement. Does this formula look familiar? What is it, do you think? Yeah, linear. So now we have 3 examples. We looked at it in the dynamics course. We saw it in electricity. Now we are seeing it in physics. In fact, you will even see it in your statics course that you will see. The same linear function. So the whole idea is find the spring rate K and the preload F0 if the following values of the force and displacement are known. So we run an experiment. So I have a spring, and I want to basically measure the amount of force that we can put on there by looking at the deflection. Can I do that in an experiment? All I have to do is just have a spring and put some weights and basically measure how much is extends. So that's what we do. Again, we measure the forces is in Newton. Measure of forces. How many of you have seen this? Newtons. Good. The deflection is measured in M. What does that M stand for? Meters, right. So 2 points, 2 deflections, 2 values of forces. What do I want to find out? What is K? Do you remember what the name for K was? It was a spring constant, right? Newton per meter, which was the units for it, and we know it as stiffness. Stiffness. Those of you who might have heard that. Spring stiffness. How stiff it is. And that's based on that K. And F0 is the initial or preload. So, method 1. Treat y as the independent variable. Independent variable. Now, wait a minute. If y is equal to mx plus b, independent variable was what? X. So what are we saying here? What we are saying is y is, just because it's y doesn't mean anything, because the formula that you're dealing with is called ky plus f sub 0. And this is the y that we're talking about, which is basically the x that you had before. Linear function. Again, y is equal to mx plus b, the linear equation that we've been talking about. Slope, delta y over delta x. In this case, delta y is delta f. And delta x is delta y. Uh-oh, I'm getting confused here. Am I getting confused here? No, because the formula is different. Again, why am I kind of mixing these up? I'm mixing it up because when you are looking at the mathematical formula, just because we're using the same parameter as somewhere else, that doesn't mean they're identical. You have to have an understanding of the physical meaning of what you are dealing with. Here we're talking about y, which simply is a deflection. Why we're saying it is y? Because most probably when I'm doing the experiment is as such that the spring is hanging upside down and I am putting some weight here which pull it down, right? And it's being pulled down in what direction? Y direction. So that's why we call it this way. Because most probably in the experiment, this is how you're going to measure it. You put different weights in there. You know, you're familiar with weight in pound, but weight is really measured in newtons, right? And when you say 1 kilogram, the kilogram, in fact, is a mass. If you want to say kilogram weight, then that means that you have to multiply it by some acceleration term that converted into 9. You see, remember, those of you who have heard that 9.81, that parameter, that's where that is coming from. Because a mass is a mass. A weight is really dependent on the gravity and the gravitational acceleration. So the force we are putting here is really delta F divided by delta Y is simply deflection of that spring. That has nothing to do with the XY coordinate. It's the deflection of that spring. So 2 points. 5 minus 1 divided by 0.9 or minus 0.1. So 2 deflection points that we measured in the experiment, and that gives me the slope the slope of a linear function. Now I want to find out the intercept. The intercept relates to preloading. The spring was preloaded. So what do you think the value of that B would? How the measurement? Is that in meters, B? Yes. Yes? Should be meters. Remember, Y is in meter. But B is not in meter because F is measured in what? Newton. So how can you add meter to newtons? You can't. So B must be in newtons, right? So we just use one of the points. And this is the value of B. 0.5. What's the unit? Newtons, exactly. 0.5 newtons. Now, do I have the formula for the line? Yes. Force is equal to 5y plus 0.5. In other words, now all I have to do, if I want to find out how much force the spring exerts or resists, all I have to do is just look at the deflection and see how much it has been deflected. Can I plot that? What is x-axis and what is y-axis? What is x-axis and what is y-axis? Yes. Okay? So that's it. So I'm now going to make you a little bit more excited. Now we dealt with linear equations. Now we're going to go to quadratic equation. What does quadratic means? Huh? Multiple terms, right. So now we're looking at a ball or something that I throw up. What happens to it? Come down, right? So I'm throwing a ball and we are identifying the height of that ball as a function of t, which is time, is equal to 96t minus 16t squared. You see that? This is called a quadratic equation. Where do I see it? Physics 1 and 2 or dynamics. You see that? A quadratic equation. How many of you have seen a quadratic equation? Right. Where do we see it? Algebra, right. So let's make some sense. Find the time when the height is 80 feet. So now we are giving you the equation of that ball. And I want to find out how long does it take for that ball to reach the height of 80 feet. So what do I do here? Yes?
You need to set it to a form so it's ax squared plus x plus whatever given number
Right.
is equal to 0.
Right.
And then rearrange so that you can solve for x.
Right. So you're basically giving the algebraic equation, right? So, but let's look at it in physical term, right? So let's say that 80 feet is here, right? And I throw this up. So, in your opinion, how many times would that ball reach the 80 feet? Huh? Twice. Right? Twice. Quadratic. So you are looking for two answers. Right? You're looking for two answers. That's why you need to have an equation that have two answers. Now, I do something else. I throw it up. What's the maximum height that it reaches? Is there two answers or one? So in your opinion, physically, think about it, physically, in your opinion, if I am plotting the curve of the height against time, because it starts in 0, is it like this? Or is it like this? All right? So the shape of a quadratic curve comes into mind. So physically now we understand it. There is a reason for it, that the shape is like this. So when I'm looking at that, you want to find out what the value of, what the roots of that equations are. So you need to do some measurement now. So looking at this, I say, so I have to put this in a form where I can solve it. So I'm saying that the height is going to be 80 feet. So if I know the height, what am I looking for? T, right, the times at which it's going to reach that 80 feet. Do you see that? So what do I do here? I simply replace for the value of h. H of t is 96t minus 16t squared is 80. Or 16t squared minus 96t plus 80 is equal to 0. Does that look like a quadratic equation to you now? Somebody say ax squared plus bx plus c. This is the quadratic equation. There you are. And you have seen that in algebra. So, what needs to be done to make this equation simpler? For us to be a yes. Right. Make it simpler. That's the whole concept. We want to make it simpler. So we simply divide it by 16. So if I divide it by 16, I end up with t squared minus 6t plus 5 is equal to 0. How many people follow this so far? Okay, those of you who do not follow, ask me a question. Why aren't you following? It's okay. You have to be an active participant, I need you to really tell me. Because the idea now is, I have an equation. Now, do I really need to measure anything here? Not really, because I have a quadratic equation. All I'm saying is, I'm looking for the value of time that basically satisfies that equation. How many methods can we solve it? Yes. 3 methods, exactly. I'm going to do 2 and I'm going to let you do 1. One is called factoring. How many of you are familiar with that? Good. So what we need to do is we have to factorize this so that the roots come out. What do we mean by factorizing? Can somebody explain to me? Yes.
Basically, the 5 would be, you just break up into 2, yeah, 2 squared.
So go ahead, say it.
Like you would put it as t minus 1 in parentheses and t minus 5 in parentheses.
So if you have,
So that when you multiply it together, they get the same equation.
so if you have x squared plus say bx plus c, you want to show this, say x minus say, I don't know, a1 times x minus a2, which is
When you multiply a1 and a2, it's together is usually
Right? So what we're saying is, now you want to find a T1 and a T2. So simply what you're saying is T1 plus T2 is equal to, and then the other one is T1 times T2 is equal to, right? What is T1 times T2 equal to?
E squared.
Over there. What is that? What should the value be?
T1 times T2.
Uh-huh. 5. And T1 plus T2?
Negative 6.
Is that correct? Remember, we're saying minus, but what we're not saying is this is actually plus. Because if it was not, then you would not have negative here. So you're looking for two numbers that when you multiply them, okay, that when you multiply them, the answer would be 5. When you add them, is minus 6. Minus 1 and minus 5. You add them, you have minus 6. You multiply them, you have 5. So here you are. What does that mean? What does that mean? Yes? Right. So when I'm throwing this up, the first time it's going to reach that 80 feet is going to be at 1 second, and the second time is going to be 5 seconds. So between the second one and the second 5 is going to reach its peak, and it's going to come down to the same number, before it goes down. Method 2, quadratic formula. You remember that? When you have a quadratic equation, x equals to is minus b plus or minus b squared minus 4ac divided by 2a. We have the value of a, we have the value of b, and we have the value of c. So all we have to do is just place it in there. We should be able to get the same answer. Now, which one, in your opinion, is easier? What's that? Factoring, right. Yes.
Well, the quadratic, factoring is easy, but quadratic formula is better because you already mix and factor.
Exactly, okay? So it may look simpler, number one, but boy, right now you're talking about 5 and 6. What if you have 2,982? Would you be able to get those two numbers to factorize it? So this would be a simpler. So what is the third option? Squares, right. So what we do is that we need to shape it, make it in a shape that on one side we have a square, a perfect square, which in this case, a perfect square, when I'm looking at it, is a t squared minus 6t plus 5. So what is the most perfect square to that? So 4, 3, 2, what is that? So we put basically that, add and subtract on both sides to make it a perfect square in order to get those two answers. So I want to look at different times now. T is equal to 0. What does that mean? At initial point, yes. Yeah. What would the height is? 0. So that means at time t equal to 0, this ball is sitting on the ground. Then the next thing is, all right, so let's try something else. This part we already have. The ball goes up and down. What is the maximum height? Where does it reach the maximum height? Now you will eventually see this. Yes? 1/2 of t? Yes? It is definitely between 1 and 5. 3 seconds? No, it just happens that way. But further along the way, as you go through your engineering program and you do more advanced math, you will find out that in order to find the peak of this curve, you need to differentiate it relative to time. And then if you differentiate it, then you can easily find that value. We don't want to go there, but that's again a mathematical tool. In this case, it was a perfect. Yes? Right. 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 Yes. So, but I mean, you don't need to know that. But what we are saying is that because right now your curve is completely symmetrical, and then if at 1 second and 5 seconds it gets to 80 height, then in the middle is going to be the second number 3 because it's completely symmetrical. Okay? So that's why we got it. But in the other thing is that what was the formula? The 96t squared minus 16t? Is that what it is? Oh, 16t squared minus 60 or plus 96t, right? And then what I'm saying is if you differentiate it, it says 32t is equal to 96, and then t is 96 divided by 32, which is equal to 3. Right, but you don't need to know that because this is more advanced calculus. But what I'm saying is that the calculus number 2 in your in your experience here is going to talk about differentiation, and that's how you're going to get these numbers. But now we're just finding it experimentally. The question is, can this go higher than 144 feet? We know that it's not because it's going to be maximum. So what do we do is, let's see. If you want to get higher than 144, let's say 100 and I don't know, I think what the example I've given here is 160. So would it get to the value of 160? We know that is not going to get there. But if I get to 160, all I have to do is just put 160 over here. So I have a quadratic equation, which is like this. Do you follow? So the answer is, okay, what is t? Look under the square root. 36 minus 40 is a negative number. Does this have an answer? That's why it doesn't have an answer. It has a complex value. That means that is why your ball is only going to get to 144. It's never going to get to 160. Right? So we are looking at the rocket projectiles, and we are measuring the initial velocity, and we're calculating the height. We can exactly know where the rocket is going to turn around. That's why when we are basically going towards the space, and at a certain point, we need to basically be very tangent to basically the Earth atmosphere, we can measure it basically based on what we are starting from. And a very, very simple formula. Very simple formula. All we have to know is the parameters. So this basically tells you some ideas about the linear equation, quadratic equation. You should be able to do the homeworks. The lectures I've given you is going to be on the blackboard. You're going to get all of this there. And if you have any questions, make sure you attend the recitations. There are 3 recitations. If you cannot attend it because of some issues, contact the instructor, let them know. But you need to attend at least one. The recitations are recorded and it's going to be available for you online. So, no excuse. Okay? Have a great Wednesday. Yes. For no, I would rather you keep it in a book.
Okay, all right.
So then for
Because I wasn't sure if we're going to collect it or not.
they are.
Oh,
Yeah.
okay.
It's going to be collected and it's going to be graded.
Okay.
Yeah.
All right.
About the recitation, it's one every week, right?
Recitations?
Yeah.
No, there's 3 every week, but you're assigned 1.
Oh, okay.
So you have it in your timetable.
All right. When are the recitations going to be put onto like our schedules online?
It is on the blackboard. Your name, if you go there.
All right, because it's not on the temple one. That's
No,
what
no,
I was
no,
asking.
no.
All right.
It's on blackboard. You have your name and it says which recitation
Okay.
time you are in. And you must have received also an email.
Yeah, I did. I just want to know if it'd be put on temple as well.
No.